Section 6 of Chapter 4 Equation of State is Thermal Equation of State. What is thermal equation of state? The thermal equation of state is an equation of state including temperature as well as pressure. Why it is important for geophysics is clear because the Earth's interior is at high temperature. The top of the atmosphere is considered about 1700 Kelvin. At the 660 km discontinuity, temperature may be 2000 Kelvin, and at the core mantle boundary, temperature may be 4000 or 5000 Kelvin. In order to obtain the density of the Earth's interior and at such high temperatures and pressures, we need thermal equation of state. There are two paths to reach high pressure and high temperature conditions, P3, V3, T3, from ambient conditions of P0, T0, V0, T0. We have the first choice is we first heat and then compress, which is referred to as HC path, and the second choice is we first compress and then heat, which is referred to as CH path. These three diagrams explains these two paths. This is on TP space, this is on VP space, and this is on VT space. The red arrows show the HC path, and blue ones shows CH paths. So on the TP space, in the HC path, we first heat from T0 to T3 at P0, then volume increase, and then we compress from P and increase pressure from P0 to P3. Here at temperature T3. In this case, volume decrease from V1 to V3. The second choice in the CH path, we first compress and increase pressure from P0 to P2 at temperature T0. Then volume decrease from V0 to V3 at temperature T0. Then we heat the body from T0 to T3 at constant volume. Then pressure increase from P2 to P3. In this diagram, we first decrease volume V0 to V3 at constant T0, and we increase temperature T0 to T3 at constant volume V3. From increase of temperature from T0 to T3, pressure increase from P2 to P3. The representative thermal equation of state following path HC is high temperature Boltzmann equation of state. As I already mentioned, in HC path, we first increase temperature from T0 to T3 at ambient pressure P0. We express this path using integration of thermal expansivity. So from temperature increase from T0 to T3, volume increase from V0 to V1 due to thermal expansion. and which is expressed by this equation. Initial volume is V0 and we integrate thermal expansion coefficient from T0 to T3. Then we obtain V1. As we have already discussed, thermal expansion coefficient increases with increasing temperature. But here we first approximate the thermal expansion as a constant quantity. In this case, volume at high temperature is expressed approximated by 1 plus alpha 0 times T3 minus T0 times initial volume V0, equation 4.6.2. If we consider thermal expansion coefficient is a linear function of a temperature, then we have volume V1 is nearly equal 1 plus alpha 0 times T3 minus T0 plus 1 over 2 alpha 1 T3 minus T0 squared times V0, equation 4.6.3. In the next step, we decrease volume from V1 to V3. Then pressure increase from P0 to P3. We express this path using third order Boltzmann equation of state in usual case. So P3 is equal to 3 over 2 power 3 over 2 times KT0 at temperature T3 times 7 over 3 power of V1 over V3. V1 is volume at high temperature and ambient pressure, and V3 is temperature is T3 and volume at high pressures after compression V3 minus 5 over 3 power of V1 over V3 times 1 plus 3 over 4 times KT0 prime minus 4 times 2 over 3 power of V0 over V3 minus 1. So again, the KT0 T is the isothermal bulk modulus at zero pressure as a function of temperature T. For simplicity, the isothermal bulk modulus at high temperature and zero pressure KT0T is assumed a linear function of a temperature. Therefore, KT0T3 is nearly equal KT0 at zero temperature plus the temperature derivative of isothermal bulk modulus with respect to temperature times temperature difference T3 minus T0. And in most cases, because of experimental difficulty, the pressure derivative of isothermal bulk modulus KT0 prime is independent from P and T. Of course, this is just approximation. So the next is CH path. The typical, the representative thermal equation of state following path CH is the Mie-Gruneisen equation of state. As I have already explained, in this path we first compress the body from V0 to V3 at constant temperature T0. Then pressure increase from P0 to P2. We express this path using Boltzmann equation of state in many cases. So P2 is 3 over 2 power is KT0 at T0 ambient temperature times 7 over 3 power of V0 over V3. V3 is a volume after compression minus V5 over 3 power of V0 over V3 times 1 plus 3 over 4 times KT0 prime minus 4 times 2 over 3 power of V0 over V3 minus 1. Equation 4.6.6. Then we increase temperature from T0 to T3. Then pressure increase from P2 to P3. This pressure increase is expressed using P, delta P, TH. TH means thermal, and delta P, TH is P3 minus P2. And this is the integration of temperature derivative of pressure at constant volume V3. And of course, the temperature derivative of pressure is thermal pressure. In Mie-Gruneisen equation of state, the pressure increase by temperature increase at constant volume is expressed using Gruneisen parameter times thermal energy increase divided by volume. So equation 4. This equation is referred to as Mie-Gruneisen equation of state. Increase of thermal energy is simply expressed using integration of isochloric heat capacity CV from T0 to T3. And this CV is usually approximated by a Debye model, and therefore CV is equal to 9 times NKB Boltzmann constant times third power of T over theta D Debye temperature times integration of fourth power of x times exponential function of x over exponential function minus y squared from and with respect to x from 0 to theta d over t. Equation 3.7.18, we have already learned it. Let us consider path HC and path CH, which can construct better thermal equation of state. Some geophysicists say a high temperature Boltzmann equation does not have physical meaning, but the Mie-Gruneisen Debye equation of state has, because the thermal pressure is expressed using the Debye model. However, I doubt this idea. Nevertheless, I consider CH path can allows us produce better thermal equation of state. The clear reason is physical properties at high temperature and room pressure conditions for HC path are very difficult to obtain, because high pressure minerals are unstable at high temperature and room pressure, and we cannot measure physical properties of high temperature, high pressure minerals under such conditions. In contrast, the physical properties of high pressure minerals at high pressure and room temperature can be obtained in many cases. because of temperature is not high. Of course, for example, gamma ion, we cannot quench it, therefore we cannot take obtain physical properties of gamma ion so easily. Nevertheless, for example, in the case of silicate minerals, we can measure elastic constants at high pressures and room temperature. Therefore, thermal pressure of thermal equation of state can be constructed using such data for the CH path. For this reason, let us argue the thermal equation of state for the CH path in more detail in the later part of this section. This is the end of the section 4, Manuel's equation of state, in chapter 4, equation of state.